To some people, this is nothing more than a country road with a little bridge over a little stream. There are more than 500,000 bridges like these scattered across America's countryside. And while they might seem to be nothing more than little bridges to the casual observer, collectively, they represent a very big problem.
More than 40% of our nation's short-span bridges are living on borrowed time. I'm Ralph DeYoung. Over 250,000 bridges like this one, which are being used every day, are either functionally obsolete, structurally deficient, or just plain worn out. The fact is that it's really a matter of luck rather than time that will determine how long it will be before they collapse.
In 1967, the Silver Bridge between West Virginia and Ohio collapsed. 46 people were killed. That one incident focused attention on the nation's bridge problem. We have approximately 575,000 bridges in this country. Of that number, 230,000 are considered to be deficient. The Federal Highway Administration defines a deficient bridge in two ways. The first category would be a structurally deficient bridge, which would include all the bridges that are restricted to light vehicles, bridges that are closed, or bridges that must be rehabilitated immediately to remain open. The second category of deficient bridges would be bridges that are functionally obsolete. That is, bridges that have clearance problems, load carrying capacity problems, bridges that are too narrow to accommodate modern traffic.
Senator Robert Byrd of West Virginia has been a leading advocate for a new timber bridge technology.
Across our country, experts estimate that roughly 238,000 deficient, obsolete, and unsafe bridges need to be replaced. Conventional concrete and steel bridges have proved to be vulnerable to the sometimes rapid, corrosive, and rusting effects of storms, freezing temperatures, and salt treatment. Fortunately, experts in bridge construction have discovered that technologically treated hardwood timbers can be used in the replacement of as much as 80% of our country's dangerous or obsolete bridges. The lifespan of such timber bridges has been estimated to be as much as twice to 3 times as long as conventional steel and concrete structures. In an effort to make available a more affordable, practical replacement for steel and concrete construction, 2 years ago I launched the Timber Bridge Initiative. And over the past 2 years, I've secured approximately $6.6 million in federal appropriations for nationwide timber bridge demonstration projects, research and development, and technical information programs. Of that $6.6 million, $4 million is designated for timber bridge construction nationwide.
Replacing bridges is costly. What the Timber Bridge Initiative has demonstrated, though, is that there are methods and techniques that are less expensive, that are more cost-effective than the traditional concrete and steel approach. Timber railroad trestles go back a long way in our country. Many of them, like this one, are still in use. When it was built, it represented the state-of-the-art technology of its day.
More than 10,000 covered bridges were built in this country during the 19th century. Many of them were handcrafted from local timber by skilled craftsmen. And then toward the end of the 19th century, even though they were still in daily service, nearly all of those wooden covered bridges were torn down and replaced by new ones made of iron. A few years later, most of those iron bridges were in turn replaced by concrete and steel. Those covered bridges that are still standing are now well over 100 years old. And the reason these old bridges have stood the test of time is really pretty simple. Their wooden decks are protected from direct exposure to the elements. And the biggest thing that happens to them is that wooden decks eventually wear out and have to be replaced. Some of the covered bridges dating back to more than 100 or so years suffered dearly from neglect, so much so that they were condemned and torn down. But luckily, a few of them are still around thanks largely to a small number of people dedicated to their restoration and preservation.
We're only replacing the deck now, which is just worn from heavy traffic. It was a laminated deck, 2x6 on edge. It was spruce, pressure treated. So we're putting down where the wheel tracks are, we're putting down oak. And instead of putting it on edge and laminating it sideways, we're putting down one piece 4 inches thick. And that'll stand the strain of the pounding better.
The Cornish-Windsor Bridge in Cornish, New Hampshire, it's the longest covered bridge in the United States, and it is the longest two-span bridge in the world. It was built in Civil War times, just afterwards in 1866, and that makes it about a little over 120 years old. It was condemned by the state a couple of years ago as being unsafe, mainly because the members underneath had broken loose from the ice, and it had a big sag in it. It was never, in my opinion, in any danger of collapsing into the river, unless perhaps a tractor trailer full of steel went over it. The timbers, as we took them apart, had almost no rot in them. I wouldn't say not almost, they had no rot in them. Very little rot was found in this bridge right from the beginning, and that was mainly in the upper timbers where the roof leaked, and it got in behind some of the cord members and some of the lattice members, and we did find a little rotting, but not much. And the lower members were as solid, not counting the deck. Now, the deck has been replaced 3 or 4 times just from wear, not from rot. But the actual structural member of the bridge had to be cut apart with chainsaws. The main point to be made here is that if, in fact, you cover wood in some way, it will last almost indefinitely. Keep it dry. Keep it from going into the wet-dry cycle. The rot that happens will not happen. Of course, you can pressure treat it also, which is going into a modern way of preserving wood.
These structural timbers have been pressure treated with creosote. They're on their way to becoming part of a technological advancement that appears to hold great promise for helping to solve the nation's short-span bridge problems.
Replacing bridges is costly. And in these days of ever-shrinking budgets, there's an ever-increasing need to explore new alternatives and new techniques for building bridges that are more cost-effective than those of the traditional concrete and steel design.
We've found that it's very important to provide not only preservative treatment to prevent the wood from decaying or rotting, but also to use a preservative which will provide a moisture protection barrier around the wood so that the wood doesn't absorb moisture with time. Creosote treatment or pentachlorophenol in heavy oil is an excellent method for preserving the wood, preventing decay, and ensuring long life expectancy for a timber bridge. There's a couple of essential things that we need with preservative treatment. One is we need preservative treatment to soak within the material around the exterior of the piece to make sure we've got a protective envelope. With small size lumber, we can get that preservative treatment to go through the entire cross-section. With large dimension lumber like this, Coast Douglas fir, it's impossible to get full penetration treatment of the member, but it is essential in this case to make sure we develop this full envelope of protection around the member. Along with getting that kind of protection around the member, we want to ensure that any kind of fabrication on the member, cutting or drilling of holes, is done before the preservative treatment. And you can see here all the holes in this member were drilled before preservative treatment, which means we've got that full envelope of protection around the entire piece of wood. As long as we can maintain that envelope of protection, we can expect this piece of timber to last at least 50 years.
The concept of stress laminating timber bridges originated in Canada. For several years now, researchers in the United States have been expanding on that basic idea to see whether or not pressure-treated, stress-laminated timber bridges can function as well as those made of concrete and steel, while at the same time being easier and less expensive to build and maintain. So far, this is what they've discovered.
Ontario developed the stress-laminated type of bridge, but when we started looking at the type of work that was done there, we found that there were some questions about what happens in a bridge when the moisture content changes. You know, the material gets wet over the course of a year and dries out, wet, dries out. And their research seemed to have some things lacking on what that would do.
Under the Timber Bridge Initiative, extensive research is being conducted at the Forest Products Laboratory, the University of Wisconsin, West Virginia University, and Penn State University.
The experiments are designed to investigate how the stress in the deck changes with changing moisture content. The deck panels are subjected to cyclic wetting and drying to raise and lower the moisture content. We're forcing rapid, fairly large changes that would take several seasons or several years in an actual bridge, so we can get the data faster.
The other thing that we found in Canada was almost all of their work had been done on small dimension lumber put together to form a bridge. Well, here in the United States, very often we find it more economical to use large, rough-sawn lumber.
We do test a number of specimens for a number of cycles and varying stress levels to establish what we call a stress versus the number of cycles curve. From that curve, we can relate to the life expectancy of a real bridge. The way we go about it is we find the amount of stress level that is induced in a bridge due to an actual truckload, and then we know roughly how many cycles that bridge is going to be subjected to over a 50-year period and see if the stress levels are going to be within reasonable limits, and this is how we correlate the long-term life expectancy of a bridge.
The real goal of almost all the research that's being done here in the United States is to develop an informational background that we can use to convince the state highway bridge engineers to accept the stress laminated system as a bridge design system. The way we do that is by preparing a very extensive background of research information, laboratory tests, analytic work, and field tests of bridges to prove that we can predict how these bridges actually behave. If we can predict how they behave, then we can tell people how to design them.
This is a unique type of bridge. It was first done in Canada as a remedial measure to tighten up the old nailed decks in the late 70s, and then migrated to the United States. And this 46-foot span at Houserville was built as a demonstration bridge so that we could actually find out how it behaves in this particular environment. I noticed while they were putting it together that the bridge actually had lost part of its camber, and it dawned on me that we could perhaps incorporate some steel sandwich plates between the timbers in such a way that we would increase the structural stiffness of the bridge and help it resist deflections due to both the trucks on the bridge and the weight of the structure itself. So I built this model, made some measurements, and found that using steel strips definitely improved the stiffness of structure, so much so that I was encouraged to try to go further with a full-length prototype. I found that, for example, putting about 4.5% of steel in will double the stiffness of a bridge. And this means that we can do several things. We can either decrease the depth, we can use smaller timbers, smaller in length and smaller in depth. We have a lot of medium-sized hardwood trees that need to be utilized. The situation in many eastern states, which has led to a timber initiative, is that timber is being produced, especially hardwoods, faster than it can be used. In spite of that, and with all of the small bridges, the thousands of small bridges that need to be replaced, we still continue to use concrete and steel.
The stressing rods that hold the bridge together are torqued to approximately 100 pounds per square inch when the bridge is installed. It is the combination of this pressure and the treatment that makes the bridge impervious to water and other elements.
This is a two-cell box girder, and we have tested this box girder for 20-foot span lengths and extrapolating that it can hold a span length of 100 to 120 feet under the major highway loading conditions. Filling this void with a diaphragm like this one to make sure that there is going to be a good amount of lateral stability as far as these deep webs are concerned. If we do not have what we call the bottom flange, then it becomes a T section. And those can go up to about 60 to 70 foot span. The major advantages is a box girder is about 3 times stiffer than a T girder. However, the T girder is easier to inspect and maintain than a box girder.
This bridge near Morgantown, West Virginia, is an example of this new technology. It was prefabricated and pressure treated at a West Virginia sawmill and then trucked to the site. Pressure-treated, stress-laminated timber bridges are the latest step forward in wooden bridge construction. Since the mid-1940s, advancements in wood chemistry and wood technology have resulted in a variety of new approaches and techniques in the design and construction of timber bridges. One of the more popular methods is the glue lam bridge, like this one being installed near Binghamton, New York.
In the late 60s and early 70s, the Forest Products Lab, working in conjunction with AITC, developed the glued laminated timber deck panel. This deck panel eliminated the need for all of the mechanical fasteners and allowed us to use the glue lam stringers at the wider spacing, but now with a much more efficient deck system. That deck system was used in both transverse configurations and longitudinal. And working as a joint effort between AITC and the Forest Products Lab, we took that to AASHTO and got AASHTO acceptance, and that became pretty much the standard for the industry. In the manufacturing process, we're able to take relatively short lengths of individual pieces of lumber, say 12, 14, 16-foot lengths, structurally in-joint them together to make what we call lamination, a long ribbon. These are then face bonded together with structural adhesives to create the finished shape. Allows the designer to specify virtually any shape that might fit his design needs, ranging from a glue laminated deck panel to a large stringer to a curved arch. It might be used in, let's say, a highway bridge or even in a pedestrian structure.
And then what we're going through now is that the latest technology, that is of the stressed deck and the box girder and T sections that are developing now, are in the same stage that the glue laminated deck panel system was maybe 15 years ago.
That's correct. We've done most of the background research. We've built some of the bridges. We've got experience under our belt, and now that's being taken to AASHTO so we can introduce that technology. And interestingly enough, although it started out strictly with sawn timbers, pieces of individual laminates, we find that even with glue laminated timbers, we can stress those into a deeper deck system and increase our span. So all these things work to the benefit of the design engineer.
The Timber Bridge Manual has been written, and I believe it provides a comprehensive source of information to engineers and decision makers in areas related to timber bridge design, fabrication, construction, maintenance, and rehabilitation. The American Association of State Highway and Transportation Officials publishes standard specifications for highway bridges, which is generally recognized by most jurisdictions in the United States as the governing code or specifications for bridge design. In the case of the timber bridge systems, we have established the National Forest Products Association Timber Bridge Task Group, which includes members of the timber bridge industry, government, and private consulting firms to assist in evaluating these different timber bridge systems and design criteria for adoption. The criteria is forwarded to the General Bridge Committee for a vote by the membership of AASHTO. After this process is complete, the information is available to private individuals and government agencies as a source of design information for the various timber bridge systems. As a part of the Timber Bridge Initiative, funds have been allocated and set aside to establish a Timber Bridge Center in Morgantown, West Virginia, and continue on with the Timber Bridge Technology Transfer Plan.
A typical bridge, when replaced with timber, will use about 10,000 board feet in the superstructure and another 10,000 if the bridge is put on timber abutments. When we multiply that by the 250,000 deficient bridges, we come up with a potential market of 5 billion board feet. If we capture 10% of those, we're still talking about a market of 500 million board feet. And that is the total annual production of all the lumber produced in the state of West Virginia. Also, the underutilized species are located in the parts of the country where we have the highest number of people and the highest number of deficient bridges.
There's new technology that makes timber bridges able to perform at modern standards and in a very cost-competitive way with other materials that you might make bridges of. And there are several advantages to applying this new technology that comes from a renewable resource, that is local hardwoods, that are in long supply. And their utilization, the ability of a landowner to sell some of those, is going to improve our forests. I've been told that 500,000 or more new bridges are urgently needed nationally. And this timber bridge concept and the initiative that pushes it can be instrumental in seeing those replaced. Now, there are some really important things about that we ought to consider when we consider timber bridges. One is that not only is it a renewable material, it's not an imported material. This, in its own small way, would contribute to lessening our balance of payments problem. So it seems to me that here's a chance to do several things at once, to improve our local timber economy, to improve our rural infrastructure and thus aid economic development, and to make our rural environment more attractive and livable, and to reestablish our ties with our past, all through an activity that's aided by what really is a high technology. So it's my hope that the research and the outreach and the demonstration that the Timber Bridge Initiative calls for goes forward rapidly and thoroughly and well.
An old man traveling a lone highway came at evening, cold and gray, to a chasm vast and wide and steep, with waters rolling cold and deep. The old man crossed in the twilight dim. The sullen stream held no fears for him, but he turned when he reached the other side, and he built a bridge to span the tide. "Old man," said a fellow pilgrim standing near, "you're wasting your strength in building here. Your journey will end with the passing day, and you never again shall travel this way. You have crossed the chasm deep and wide. Why build you a bridge at eventide?" The builder lifted his old gray head. "Good friend, in the path I have come," he said, "there followeth after me today a youth whose feet must pass this way. This chasm which was but naught to me, that to that fair youth might a pitfall be. He too must cross in the twilight dim. Good friend, I'm building this bridge for him."